dispersive intermolecular forces can at times be competitive with electrostatic intermolecular forces, things like dipole-dipole or hydrogen bonding interactions. So for example, if I ask you what intermolecular forces are occurring between oil, and here we can see the chemical formula, I believe this is for canola oil, and water. If we put these two things together, observationally, we would see a heterogeneous mixture occur because the oil is going to float on top of the water. My question to you is, what intermolecular forces occur between oil molecules and water molecules that lead to this heterogeneous mixture? All right, welcome back. Hopefully you took the time to kind of observe these molecules and pick out what intermolecular forces stabilize these molecules. Now let's start with an observation of this very long oil molecule, where at the vertex of each of these like little triangular points is a carbon. And each of these carbons is also going to be surrounded by the necessary number of hydrogens to complete their octets. So each of these central carbons is also going to be surrounded by a certain number of hydrogens. I'm not going to spend the time to illustrate each and every one, but you get the picture. Each one of them is going to have a complete octet. Now, carbon to hydrogen, as we have already talked about, is a non-polar bond. So within this oil molecule, we have a polar section where this one carbon bonded to oxygen, or this carbon bonded to oxygen, is going to result in a polar section. However, the further and further we get away from that polar section, the more and more non-polar our molecule begins to appear. So we would say that we have a polar section on the left, this little section, and the rest of this molecule is going to be predominantly non-polar. So we actually have two natures existing within this one single molecule. It's like the dichotomy of man, only it's the dichotomy of molecules instead. Well, if we allow for two options, let's say either another water molecule or another oil molecule is going to approach this oil molecule, or a water molecule will approach this oil molecule, which is going to be more stable in interacting with the oil? Well, if we illustrate like a water molecule approaching, water we know, again, is a very polar molecule, and it's capable of forming a great number of electrostatic intermolecular forces. Things, again, like those dipole-dipole forces, etc. And so the polar nature of this water molecule means it's going to be stabilized predominantly by forming the electrostatic category of intermolecular forces. And so water would be able to interact with the oil, but only in this one little section. A water molecule would only really be able to stably interact with this section here on the left. This water is going to form probably a dipole-dipole force, hydrogen bonding if it's with this little OH specifically, but really we'd only be able to form like one or maybe two stable intermolecular forces between water and this oil molecule. And technically, yes, we could form probably an induced intermolecular force, an induced dipole force over here on the right-hand side, or maybe even some type of weak dispersive interaction here on the right-hand side. However, if we contrast that option with the addition of another oil molecule, OH to carbon, double bond to oxygen, and I'm just going to draw a big old ziggy-zaggy, because who got the time? The oil molecule here is going to have the exact same construction with a little polar section here and a huge non-polar section here. Non-polar bonds are predominantly stabilized by dispersion. The electrons are not being pushed in one direction or another due to the polarity of the bonds. The electrons are allowed to more freely fluctuate. And because the electrons are able to more freely fluctuate at close distances, what we're going to end up with is a area where dispersion is going to be more likely, right? We're not going to have electrons being pulled into the center of the carbon or held too tightly to the hydrogen, which is going to allow for an easier means of dispersion. But we're not just going to get dispersion between these two single hydrogens. No, no, no. Anywhere where the hydrogens are going to be coming in closer contact with each other, hydrogen here, there's going to be plenty of locations across this entire non-polar tail of the oil molecule where we can end up with long-distance dispersive interactions illustrated here. So between forming one or two stable electrostatic intermolecular forces with water, or forming a large number of dispersive and stabilizing interactions between these two different nonpolar tails, oil, as it turns out, is way more stable interacting with other oil molecules. This is because the construction of the molecules are much more similar, and again, we're going to be able to form a ton of attractive dispersive interactions. So oil is going to want to stick with oil, hence why we see oil floating on top of the surface of water. Now, oil and water can, again, somewhat interact with each other. It's not to say that the interactions between these little polar sections of the oil molecules and the water are completely non-existent. That's what allows for this stable interaction between oil and water. We do not see a chemical reaction occur between oil and water. The two just kind of hang out one on top of the other. However, this attraction is not so strong so as to lead to a homogeneous mixture. Instead, we end up with a heterogeneous mixture. Oil sticking with oil through the formation of dispersive interactions, and water sticking with water because we can increase the number of really stable electrostatic intermolecular forces.